Lecture 3, Forecasting, Section 2, and this is the last part of the pre-recorded videos for Section 2. In the previous part, we had a general method for a time series with trend and seasonality, and in that general method, we need to recalculate the seasonal factors from the scratch anytime that we have new data available. So because of that, here we are going to have Winter's method, and Winter's method would simplify the updating of the seasonal factors anytime that we have new data. And the Winter's method is actually a triple exponential smoothing method. Here is the model of the Winter's method. So as you see in this figure here, we assume that we have a trend and seasonality in our time series. So the mu here is the base. As you see here, mu doesn't have the subscript of t. So it's a constant, and it's the base signal or the base intercept at time 0, excluding seasonality. So yeah, here like the general procedure that we had in the previous part, at first we need to deseasonalize the time series and then apply the Winter's method. And at the end, we'll include the seasonal factors as well. So yeah, mu is the signal, the base signal or base intercept at time t0, and gt is the trend or slope component at time t, as ct is the seasonal factor at time t, and epsilon t is our error. Okay, and the seasonal factors SCT will be calculated like before in a way that sum over CT should be equal to N. Okay. The Winter's method is actually a triple exponential smoothing method. So we'll have three exponential smoothing equations and three smoothing factors. So yeah, we'll use the exponential smoothing equations to update the estimates of deseasonalized series, the seasonal factors, and the trend. Okay, so for the series, the current level of deseasonalized series ST will be updated by this exponential smoothing equation. So as you see here, we divide the dt, the actual demand, by the CT minus 1. So CT is the seasonal factor, right? And so why we are considering CT minus 1, let's have an example here. Let's say our season includes 4 periods. So period number 1, 2, 3, 4, and then 5, 6, 7, 8, and so on. So this is the first season, and this is the second season, right? So period number 5 is the first period of its season, right? So by assuming that t minus n, so here n equals 4 because each season includes 4 periods, right? So ct minus ct minus n here for period number 5 becomes c5 minus 4, or c1, right? This means that period number 5 will be like period number 1 of the season, and then 6 like 2, and so on, right? So yeah, by having t minus 1, actually we are considering the appropriate seasonal factor for period t. And so yeah, here at first we deseasonalize the actual demand, and then we multiply this by the alpha, and then st minus 1 plus gt minus 1 will be our forecast, and by multiplying this by 1 minus alpha, so we are taking a weighted average between the deseasonalized actual demand and its forecast. So that will be ST, And uh, the trend here will be updated in a similar way of Holt's method. So yeah, GT will be beta times ST minus ST minus 1 plus 1 minus beta times GT minus 1. Okay. The third equation that we have here is the exponential smoothing equation for seasonal factors. So as I said before, we're not going to recalculate the seasonal factors anytime that we have new data, and instead we will update the seasonal factors. So the seasonal factor for period T will be updated by this equation. So here we have a new parameter, a smoothing parameter, gamma. So this gamma is the smoothing factor or parameter for seasonal factors. So dt divided by st will be the actual demand divided by the forecasted series. So it will give us somehow an estimate of the seasonal factor. And then we have previously obtained the seasonal factor, which is ct minus n. So we are taking a weighted average between these two, and it will update the seasonal factor for period t. Okay. Now at the end, by having the factors and parameters, we can make our forecast. So let's say we are at time t and we want to make a forecast for tau steps ahead for t plus tau. So this will be, it will be this st plus tau times gt, like the method that we had for the Holtz one. So an intercept plus its slope for tau steps ahead. Okay, and at the end, since it's deseasonalized, we need to multiply the forecast by the seasonal factor, which is c t plus tau minus n, and then at the end it will be our forecast for original data by assuming the seasonality here, like seasonality. Okay, so here we assume that tau is less than or equal to n, but if tau is greater than n but less than or equal to 2n, then we need to consider the ct plus tau minus 2n, and if tau is greater than 2n and less than 3n, it will be this ct plus tau minus 3n. Okay. So now we have the procedure of the Winters method, and we just need to see how we can initialize this method in order to start from an initial point. So the initialization here means obtaining the starting values for the series, which is S0, the slope G0, and the seasonal factors, okay, C minus n through C0. So in Winters method, it's recommended to have at least two seasons of data for initialization. So here, if we assume that we have exactly 2 seasons for initialization, so this means that let's say one season, for example, and the second season. So here we are here. So this is t equals 0, and demand will be d0. And so if we go back, this period will be minus 2n plus 1. Okay, d minus 2n plus 1. So yeah, see here we're assuming two seasons in the early periods as the periods for learning, for example, yeah, for learning, and we are going to initialize our Winters method by these two initial seasons. Okay. So in step 1 of the initialization procedure, we calculate the sample means for the two separate seasons. So yeah, here we assume that we have 2 seasons. So V1 will be the sample mean for the first season, and V2 will be the sample mean for the second season. Okay, so by having these two sample means, in step 2 we can define the initial slope estimate G0 as this: V2 minus V1 divided by N. Okay, I'll show this how it works in the next slide in a graph, but if we have more than 2 seasons for initialization, then same as the above equations, will obtain the sample mean for each season. So let's assume we have m seasons here, and then G0 will be this: Vm minus V1 divided by m minus 1 times n. Okay, so let's consider this figure here. Yeah, as you see here, uh, let's say this is our first season and this is our second season, right? So as you see here, the V1 will be the sample mean for the first season, and V2 will be the sample mean for let me show it here. Yeah, V2 for the sample mean for the second season, and then V2 minus V1 will be this. Let me show here. Yeah, so here is V2 minus V1, and this will be the N, right? So yeah, as you see here, V2 minus V1 divided by N will be an estimate for the slope here. Okay. In step 3, we will estimate the value of series, the intercept at time t0 by this equation. So we consider the sample mean of the second season plus G0, the estimate of the initial slope, and then multiply this by n minus 1 divided by 2. Okay. And in step 4, we will determine the initial seasonal factors. Okay, and to do so, we'll have 3 sub-steps A, B, and C. Okay. In sub-step A, we estimate the initial seasonal factors, and we do this by dividing each initial observation by the corresponding point along the line between V1 and V2. So this is our equation here: dt divided by Vi minus n plus 1 divided by 2 minus j times G0. Okay, so what's I and j here? So we have let's say 2 seasons, right? So I will be 1 and 2. When I is 1, this means we are considering the first season, and then I equals 2 will be the second season. So anytime that t is between minus 2n plus 1 and minus n, this means we are in this first season, so I will be 1 there, v1. And if t is between minus n plus 1 and 0, this means we are in the second season, so I will be 2. Okay, and j is the number of period in each season. It will be, for example, if we have 4 seasons, 1, 2, 3, 4, the first season, and again the second season, 5, 6, 7, 8. So if we are here, I equals 1, and then j equals 1, j equals here 2, the second period, j equals 3 for the third, and j equals 4. And when we go to second season, I will be equal to 2, but j for this, j will be 1. For 6, j will be 2, right? The number of period in the season. Okay, so yeah, by having this, we easily can obtain the initial seasonal factors. Okay, then in substep B, we need to take the average over the seasonal factors. And here we're assuming we have 2 seasons, so these will be the equations for taking the averages. Let me show how this is applied by an example. Let's assume that we have seasons of 4 periods. So season number period number 1, number 2, 3, 4, the first season, and then 5, 6, 7, 8, the second season, and then 9, 10, and so on, the other periods. But here we are going to consider the first 2 seasons. The first 2 seasons as our initialization periods. So by doing that, this period number 8 will be our time 0. Okay, yeah, t equals 0 to current time. Then this will be -1, -2, -3, -4, -5, -6, and -7. So as you see here, since n equals 4, then for example, -2 plus 2n plus 1 will be -2 times 4 plus 1 will be -7. It will be, let me show with a different color here. Yeah, it will be this number, right? Yeah, it will be this number, right? So this is the first period in the season. So the like period in the second season will be -3, right? Yeah, see, minus n will be, which will be -4 plus 1 will be -3. So we are considering these two together and take the average between these two parameters, I mean for as the seasonal factors, and then these two, and then these two, and then these two, right? So this is how we take the average for the like periods for the seasonal factors. And at the end, we need to normalize the seasonal factors, and we do this by dividing each seasonal factor by the sum over the seasonal factors. And since we want to have the sum over the seasonal factor should be equal to n, so at the end we need to multiply this by n as well. So this is how we obtain the initial seasonal factors. Okay. The procedure that we had in the previous slides is one of the methods can be applied here. For example, we can apply linear regression for the baseline data if we are assuming the first 2 seasons or more than 2 seasons as the baseline data for learning. So we can apply linear regression there and obtain slopes and intercepts as we did in the Holtz method. And then the seasonal factors can be obtained by dividing each observed demand by the corresponding value of the regression model, and then we take the average on over the same period, and then we do normalization like before. Okay. And yeah, also seasonal factors can be computed by the moving average method like we did before in this part. Okay. Here we have an example, and I ask you to try to solve this example by your own, and we'll solve this example in our live session on Tuesday. So you may do practice, and then we will have this example in our live session. Okay. So as a conclusion and discussion for chapter 2 of the textbook or lecture 3 of our course, which is about forecasting, the method that you have learned in this chapter, I can say, are the most simplest one. So there are many sophisticated models, and if we have a long history of data, we may have to go with the more sophisticated models like the Box-Jenkins method, filtering theory, neural networks, and Monte Carlo simulations or other models. So yeah, as you see here, there are several models, and in the practice, if we want to choose one of the models to apply in our data set, so we need to consider the characteristics of the history of the data and also the context of the data to see which model will be an appropriate choice for forecasting. Okay. So yeah, that's it, and we are done on this chapter. So uh, so hope you see all in our live session this week, and we will have some examples there to see how we can apply the models that we have learned in this chapter. And for sure, you can use Excel for the calculations. And yeah, I mean, you can use Excel for the questions you have in your assignments and also in the tests. Okay, thank you.